Good morning, everyone. My name is James, and it is my pleasure to introduce our next speaker. I believe this is Saul's third PyData appearance, so I'd like to give a round of applause for Saul Diez-Guerra.
Thanks, James. He tried. We worked on the car here to get him to say my name correctly, but you can't do that. All right, okay. Cool, so yeah, my name is Saul Diez-Guerra. That's good enough. And we're here to talk about speed without drag, which, as you will come to find, it's a lie. I'm an electronics engineer who somehow majored in CS and somehow ended up building web applications. But most of what I did for the past 3 years has been building Python backend systems that are heavily numerical for advertising. And so, it's not the first time I need to speed my Python. Last year, I gave a couple talks, as James was saying, on Numba, which we will talk about shortly. After the talks, there was always the question of, okay, this is great, it just sounds like it might work. What else is there? What else can I use? Am I just limited to this? So I decided to, take a step back and try to get a little more comprehensive about the options you have to speed up your Python when and if you do. So with that being said, let's just start. And I'd like to start. The talk is about how what tools, what libraries and tools are available to you so you can escape the safety of Python. But the first part of the talk is going to be about trying to get you not to do that. And so, whenever you bump into the whole, oh, my code's too slow, this batch process I was doing is taking too long, I would advise to think first and try not to jump the gun and try to put it on the GPU just for kicks, right? So I think that's important. That's something that you need to check yourself first before you start going down some rabbit hole. So what if instead of using Numba or using something else, you thought it through and refactored code that might not be performant because you wrote it in a small period of time? What if you threw money at the problem? Maybe it's easier for you to just throw it on easy to parallelize it and in a really simple fashion and call it quits. Of course, evaluate the cost of opportunity because you might need to do something better with your time than deal with multiprocessing, OpenMP, whatever it is you need to do to actually speed up your code. Or you can just blame it on GIL, Vanarosum, and switch to Java. So as I was saying, first I would advise to rule out other problems. And this is broken. Wait a minute. Yeah. Okay. Okay. Fine. So what if you fix I/O problems you have, I/O bottlenecks, serializing, something else that isn't really computation being slow? Because if your computation is not being slow to begin with, the things we're going to see here today won't really help you. If you have a DB access that's dragging you down, you can apply all the NumPy you want. It's not going to help. Again, write your code in ways that make sense. Don't compile a regex over and over. Don't do stupid things that you might overlook. Don't compute anything you will discard, of course. The tools you use, make sure, like randoms. You might not need as many random stuff as you think you need. And many other things that we won't talk about today, but I'm sure you all know a bit about. There's a link to, oh, by the way, let's go back here. I uploaded this IPython notebook to that URL in case you want to access it here now or later, including the link that we just bumped into, which is a link to a talk by a man named David Schachter. And let's see. And he talks about speeding Python up to, I think it was 114,000 times. Completely different approach to what we're going to discuss today. So it's mostly, really low-level, hands-on stuff. Completely different approach, but worth taking a look into and worth keeping in mind as well. As far as CPython goes, capture the low-hanging fruit. Use multiprocessing whenever you can. Realize that for the most part you're only using one core, so if you can add that and the overhead doesn't kill you, you will automatically get speed gains. Amdahl's law might bottleneck you at the end of it, but that's fine. Do things like checking that you're not repeatedly creating temporary storage that you don't use and you have to discard and it's just not performant. Use obscure, quote unquote, language features like slots that will help you bring your, for example, slots will help your objects be smaller, thus faster. Use comprehensions with fast append. Use generators. I'm sure most of you by now have heard James' talks on generators. They're really helpful when you bump into speed problems. But especially if you're listening to him, don't use his code. But that's not the point of the talk. The point of the talk is to actually go over libraries and tools that will help you circumvent the safety of Python. Because what we have to understand is that whenever we use these things, for the most part, the tools are trying to help us not shoot ourselves in the foot, but you're basically giving up a lot of the nice things that Python does for you once you start going down this path. So speed with no drag, without drag. Let's just claim that it's speed with limited drag. We're gonna go over plenty of tools, such as exhaustive CPython that we already did, SciPy, NumPy, Numba, Parakeet, NumExpert, Theano, PyPy, NumPyPy, Cython, Blaze, Pyston, and finally Python, who Maddie will talk later about. The way we're going to do this, not sure if it's a good idea or not, but it's too late to recalculate, is by using a driving example. I wrote a really simple function that calculates the area of a polygon based on its coordinates. This is a really simple. This is a really simple piece of code that can get really slow as you come up with complex polygons. And so we're going to see how the different libraries and tools deal with it. As a disclaimer, James was saying yesterday how measuring libraries and tools under speed with a limited example and in a limited way, because some tools, for example, we're going to be using Theano on this without GPU support. It's really unfair for us to compare Theano in that way. But this is more a general walkthrough of what the options are than anything else. So let's start with your normal case, which would be using CPython, period. Can we see that? I guess. So what we have here is a generator that will create the coordinates to a polygon that looks basically like a bunch of stairs. And we're going to be generating polygons that are, I think, 200,000 steps, which comes to about around 1 million coordinates. So that's just that. And this is actually the function that you would write in CPython at the first attempt. The way you get to the area is basically adding up the result of multiplying x sub 0, x sub I times y sub I plus 1 minus y sub I times x sub I plus 1, and dividing that by 2. So that works. And if we run that with a 200,000 step polygon, which is again around 1 million coordinates, we get around half a second, which is fine. Obviously, this is for the sake of the talk, but we could get it to be really, really slow if we wanted to. So let's see what the libraries and tools we're about to discover do with it. So, small note on CyPy. CyPy is not something that we would use for this because the calculation is really simple. But depending on what you do, CyPy, as you all know, it's a library that has CyPy, the library, not the stack or the project as a whole. It's a library that has lots of helpers. So depending on what you're doing, you might benefit from looking into what CyPy has to offer there. So what we are going to use from the CyPy stack, though, is NumPy. As you all know, it's the n-dimensional array library from CyPy. And just by loading our coordinates in a NumPy array, we will get some benefits. And yeah, as you know, it's a project that's been around for a while, and the way it helps us escape Python's safety is by going down to CM Fortran when it needs to. So to use NumPy, we created the array, and then we write the functions. I don't know if people can see this, but Python notebook won't really zoom in. Anyway, what we're doing here is basically indexing the array and selecting the columns, and then doing vector the same exact calculation, only vectorized. And in doing that, we go from 1/4 of a second to close to 9 milliseconds. So that's something, really easy, and the speed up is obvious. Some other things we can use are Numba while using NumPy as well. Numba is a just-in-time compiler of Python that uses LLVM as a backend to speed up your Python. What that means is Numba will read your Python. It will build a syntax tree and translate that to the intermediate representation of LLVM, which is a modern C compiler, and then Numba will use the LLVM output to run your code. So basically, you won't be running Python anymore. You will be running generated machine code from LLVM instead. As I said, this happens in just-in-time compilation, so it's pretty fast. Some other things to mention: it has experimental CUDA support. You can compile your methods and your classes through PyCC, so you can have actually them. You can do away with the JIT and have it statically compiled. And for the folk that need GPU or multi-core, Continuum has a paid service called Numba Pro, part of Accelerate, I think. And there's a link there to the Numba talk I gave last year. In case you're not entirely bored with me now, you can continue learning about Numba there. For now, we're just going to see the most immediate example using Numba, which is basically creating a new function that's decorated with the JIT or out of JIT method of Numba. And as soon as we run that method, Numba will JIT the code, analyze it, and basically switch the results live. By doing that, we go from 8.5 milliseconds to 8, so it's not a big speed up. Obviously, NumPy is really optimized to begin with, so it's hard to make it better just by analyzing it. Although, depending on what you do, you will be able to get Numba to speed up NumPy in some fashion. Unrelated to the shoelace example, which is the name of the calculation, I wanted to mention a really nifty feature of Numba. For those of you who deal with ufuncs, usually you can create custom ufuncs and have them vectorized. You can also do this with NumPy, but the NumPy result is not as great. And we're missing a Hamlet there. Okay, so here we're basically doing a square on an array. If we do it with NumPy vectorized, it takes 200 milliseconds. If we use the square in NumPy and then add 1, and it takes way less. And if we use the Numba vectorizer, it's slightly faster. So that's something to consider, especially because, in this case, given that example is quite simple, NumPy had a square method that's obviously really performant, but depending on what you're doing and what your ufunc does, you might not be able to do that, and you might have to use this or something else. One other library somewhat related to Numba is Parakeet. Parakeet was originally basically the same sort of LLVM mechanism, but somehow along the way turned into specialized implementations of many functions manually. Instead of programmatically trying to infer what your code's doing, Parakeet implemented many functions natively. And finally, they changed their backend from LLVM to C. And they are also using OpenMP by default. Also experimental support for CUDA as well. Same thing as Numba, really simple application mechanism once you have your code in place. You decorate it with the JIT method, and then you just run it. And we can see how we went from, well, this particular run, it's slightly weird because, oh, no, yeah, I guess it makes sense. So what happens here is we decorated both the vanilla CPython code, which unfortunately gets slower, which probably means that Parakeet can't really tell what's going on, so it just wastes its time. And then when we use the NumPy version, they can actually tell, and it goes down from 8.5 to 1 something milliseconds, which is crazy. And I believe it's the best result of all these tests. One thing that you really need to take into account for both Numba and Parakeet is that there's a lot of work building the AST in a way that makes sense and in a way that they can actually do something with it. So depending on what your code does, depending on what lexical Python things you use, they might not even be able to speed it up. So in this case, by just feeding the normal vanilla CPython, we don't get anywhere. It's the same. I don't know if I have it, but it's the same result for Numba as well, which probably means that you would probably have to annotate types, or actually no, I tried annotating types and it didn't work either. So I don't know what you would have to do, but you would have to hint at both Numba and Parakeet to be able to speed up that one. One other thing we can do, and this is something I'm really excited about, is NumExpr. This is a PyData project led by my fellow countryman, Francesc Altet. And what it does is it evaluates your vector expressions and feeds them to the processor in an orderly fashion so that the cache is maximized. And they also avoid creating intermediate values. So think of it as something similar as the typical string concatenation example. They have support for OpenMP and for the vector math and kernels. If you need to do work with transcendent expressions. It's the evaluated code is not that. The evaluated expressions are not that. Wide. It's not a huge set, but it's really useful. And you will usually see speedups from about 5 to 10x. What we do is, as you can see, we have to index the array preemptively because we can't do it in the evaluated expression. And then we just write some sort of normal expression including the sum. And NumPy was 8.5. This is 2.5, which is pretty good. What else? Theano. Theano is probably the oldest library here, other than SciPy. It's a really complex library that does many things, and it's probably the one that's represented the worst here. So what they do is they define the expressions the same way NumExp will do, only in a more language semantic way. But the real deal here is, and what we won't get to see, is that they have seamless GPU support, CUDA, and lots of optimizations for really obscure things. It's tricky to install because it's a lot of moving parts. Anaconda will help you with that if you need help. For this example, you can see how we can create vectors with the tensor and just define the expression. Once you do that, you can run the function that results in the same way. And given that it's not its forte really, the result is one order of magnitude, slightly less than an order of magnitude faster than vanilla CPython, but not as good as NumPy or NumX. What else? PyPy. As you know, PyPy is an implementation of JIT implementation of Python. That's a complete standalone, separated from CPython. And it's pretty mature. It mostly works, and NumPy has a class in there called NumPyPy that works. So if we were to run this same code, this is outside the IPython notebook, but if we were to run this code, this same code we've been running, we would get this result, which is really, really good. That is, if I'm not mistaken, less than a millisecond. So I guess Parakeet wasn't the best after all. But that's the Python version, which is awesome because we didn't really do anything. We wouldn't have to do any work. If we wanted to use NumPyPy, you can go to that URL to check the support for it. If we wanted to use that, what we will find is that it's slightly less. It's not as fast as PyPy, as regular PyPy. So I guess they'll have to keep working on that. But it's all in all, both PyPy and NumPyPy are valid options if that's what you think is operationally best for you. This is the same exact code run on IPython notebook. So I missed a slide. So basically, we have the normal code that takes, in this case, there's an order of magnitude difference here, because I had to downgrade the 200,000 steps to just 2,000. So the numbers might be skewed. What that means is that PyPy is still slower than both CPython and NumPy. And NumPyPy is slower than NumPyPy by a little. By little in the case of PyPy, by a lot in the case of NumPyPy. There was a slide comparing them, but somehow it got misplaced. All right. Other than that, we've got Cython. Cython is the Python implementation on the JVM. It's pretty easy to install, and it was pretty seamless to actually get it to work. The code run more or less in the same time, so it didn't really speed up that much. That's the slide I was talking about. We can see how NumPy and CPython is really fast. PyPy itself is really fast. NumPyPy is getting there, and Cython just works as well or as bad as CPython does. New things to just keep track of but not really use. Pyston. Pyston is a new implementation of Python that Dropbox is working on. It's heavily based on the LLVM. You could say it's somewhat something like Numba or Parakeet, but in the entire language scope. No tracing, conservative garbage collection, calls being made. And they're doing the one thing that I'm eager to read more about, which is they're basically coming up with both machine codes with type prediction and as a fallback, and they're branching between them two depending on the result live. So that's pretty interesting. Unfortunately, it's really green. It's really new. It doesn't even work on OS X. So we'll see where it goes. Blaze. I don't know if Travis spoke about Blaze in this conference, but Blaze is the new NumPy, or will be someday. It's a cloud big data NumPy. Yes, please, cringe. And it will help you do whatever, all the things that NumPy helps you do, only with support for large distributed and heterogeneous data sets. Lots of adapters to get that to work seamlessly. And that's a URL. And you know, when all else fails, you can use C extensions, Cython, C types, and CFFI. At that point, your drag is more than apparent, so you're on your own. I wanted to talk about Python for a second. Python is the next talk. Mehdi will be talking about what Python is and what it does. But it's basically a transpiler that takes your Python into modern C++ through annotations, like we saw with Numba and Parakeet. It's got some interesting support, and it's pretty exciting. So I'm really looking forward to hearing him. And that's basically how it looks, which is exactly the same way Numba and Parakeet look. So to recap, there ain't no such thing as a free speedup. So keep that in mind. Think first. Try to avoid going down this route because it's easy, but it's not that easy. And just choose whatever it's best for the job. Thanks. Or
So I have a piece of code that is generated into Python. It's serial code that just a bunch of ifs, some computations and assignments, nothing very complex. From all of those tools, which one should I use?
So the code is really simple.
It's automatically generated by a system.
Oh, it's automatically generated.
Yeah, it's Python code that's generated out of something else.
Yeah. And what's the kind of data that the code uses?
It's computations. Basically, it's Monte Carlo simulation compiled into a Python file.
Can it be vectorized in any way?
Not really. It's spaghetti code, really. It's just this value, this parameter gets this expression, and then several ifs. That's it. And it repeats itself many times. It's really spaghetti. It's nothing very complete. Nothing very intelligent.
Yeah, that's interesting. So if it's not really, if it's mostly scalars, it's interesting because most of these tools will help you speed up things that are, arrays basically. So I wonder what the performance gains would be with just scalars. I would say try PyPy first because it's a entire language optimization.
It fails it failed in the past on some things, didn't pass.
Then it might not be that simple, right?
I think it was some library or something, because I do use math libraries if I recall. I don't recall, it was a long time ago. But
okay. In that case, I'd say try with Theano. isolate, especially with really excluding PyPy and Cython and Pyston whenever it comes out and whatever. When you're just using libraries, you should try to isolate the part of your code that's being slow, and you should try to speed that up. That part. I would do that. I would isolate the slow part, and try with Theano probably. But if you're basically being blocked on results coming from third-party libraries that might not be as simple, you might not be able to leverage these things.
So you're telling me that there is no easy way. This is what you're trying to tell.
If you depend on third-party libraries that are not that simple, then no. If your code is just a bunch of if and else's and normal types, I would say use PyPy, use try Theano, but really if it's that simple, just write it in C.
Okay. Thank you.
3, 2, 1. Thanks. Oh, sorry.
For the Cython numbers, did that include the time to start up the JVM? Was it a cold start?
No, that's I was using the Python timer, so I would assume that it didn't include that. Which, yeah, that's a good point. Right, thank you.